So now we have Zamir Filho, cutaway applied to corner point models.
Okay, hello everyone. My name is Amir. I'm from the University of Calgary, and I will present to you the paper called Cutaway Applied to Corner Point Models. I also would like to say that I had the opportunity to work with Felipe de Carvalho and Ricardo Marroquim from UFRJ, and also Emílio Vital Brazil and Mário Costa Souza also from University of Calgary. So the outline, before to explain my motivation, I need to talk briefly about the domain background. After this, I will talk about the geometry called corner point. So we will go through the application workflow, the cutaway itself, which is the technique that we applied, and then we will go to the results and the conclusion. Okay, our application is concerning about the oil and gas exploration. In the oil and gas exploration, we have many subdomains working together, sometimes in the same phase, sometimes in different phases. And in a higher level, the final goal is to achieve the maximum oil and gas recovery. But in a lower level, the reservoir engineering and the other disciplines involved need to provide a reservoir model which will be as close as possible from the actual reservoir that we find on the field. So here it's more or less the reservoir model that we work after the simulation. And also, if you keep working calibrating the model, you also keep work with the geometry. Okay, here I put some data types just to give you a general idea about what the reservoir model. Here in the middle, we have the reservoir model, and it's a combination of all other data. For example, here we have the outcrop, so the geologist can get like rock properties about it. Here we have the seismic, which the geophysicists are able to identify the horizons, the faults, and probably some oil and gas fluids information. Here we have before to have the simulation, we just have static properties, which means that we don't have properties which varying through the time. All of them are pure statics. So after you generate the simulation, you have, apart from the static properties, you also have the dynamic properties. In other words, now some properties may change the values among the time. So our scope will be to have this reservoir model already generated, and then we work with a data called well test data, which is a measurement that reservoir engineers do in the field. They get like information about the property, the pressure varying through time, and then they are able to calibrate the model because, as I said before, the dynamic properties up to now were just generated synthetically by the simulation. In other words, the reservoir engineer inserts some parameters and generate like the dynamic variance according with his input. It's not real data. So here, for us, the well test implementation will be just a 2D graph. In the x-axis, it has the property value, the time, and in the y-axis, it has the pressure values. Sometimes it also has the derivative. And here we have the reservoir model that we implemented, obeying the geometry which is called the corner point model, which I will explain later. Okay, so first, when the reservoir engineers start to work with a geological model, a reservoir model, they start using the Cartesian coordinate system, but as it's so regular, it doesn't allow you to fit the boundaries of the reservoir well inside it. So after some years of research, they start to use a non-rectangular coordinate system. In this case, it's called corner point because it has the corner. Each cell has 8 corners, and it also has pillars, but unfortunately, we don't have time to explain a lot about it. So an important feature for the corner point compared with the regular Cartesian is that it allows for you to have discontinuities. In this case here, we have a fault here, and here we have a layer, and the same layer here, but they are not being connected by this point. In this case, we have both of these corners has the same IJK index, although they have the different X, Y, and Z coordinates. Here we have the real corner point model with a fault inside. As in this moment, we are just concerned about the value properties within the cells. We don't care about the fault itself. We just care about the geometry and its values. Here in the initial, it's important to say that for the reservoir engineer, this application, it's important to correlate this data with this one in order to calibrate, as I said before. There's no software up to now that does these correlations because the software are worried about more big picture instead of going to details. So we decide to use a filter concept. So the user, with these sliders, the user is able to select a range of properties. And based on this, the cells which falls within this range will be selected. As I show here. So here, those cells are the cells which the property, this property is between this range of values. Sometimes the value is not like direct calculated. Sometimes you need to apply a difference in values. So you have the range varying through the time steps, and you need to calculate this difference and check in all time steps to see which cell has this variation in each moment. The heuristics for this will depend on the reservoir engineer. Oh, sorry, I forgot to mention. Well, as we eliminated the other cells, it was important for us to draw just the boundaries, just the general geometry of the reservoir to keep the context and also the focus. It was like a requirement for us to keep this in all filters. So we have a second filter, which works in the same way. We have two sliders. We have a region inside the sliders. And based on this, we will have another focus and context. In this moment, we have the context, which are the cells with a bit of transparency. And the focus itself is a cell which has full opacity. It's very important for the reservoir engineer to be able to verify the color within the cell and to map according with the legend. Otherwise, he will not have, if he cannot see the real color, he will not be able to see the real value, the real range about the cells. So as a solution, and as here, we have many blending according with the many layers that we have as we apply transparency. The color which we are seeing here is not the real color of the selected cells. As a solution for this, we decided to implement cutaway, which in this paper, Bbbb defined the cutaway as an NPR technique because it came from the illustrators. And the subclass that we implemented was a breakaway technique, which needs to obey 3 rules. First is that the primary object must be distinguished from the secondary object. The second rule is that from any given viewpoint, you need to be able to see all the objects. And the third rule is that you need to define, the third rule is that there should be just one hole for the whole primary object. Our general approach is that as we are working with discrete cells, we trace array from the camera to the selected cells, and based on this distance, we eliminate or not the unselected cells. In other words, the cells which are transparent. Okay. So here we have, before we have this, in other words, we are not able to define the exactly color based on the scalar here. And now, with the cutaway, we are able to see the exact color. And when we change the camera position, all the 3 rules must be respected, as I said to you before. So here we have the same selection. We just changed the view position. And although the primary objects are the same, the selected cells need to be updated. Here, we changed just the aperture angle. which means that the region around the primary object was expanded. Okay, here is a small video, and then I will finish the presentation. Iterativity works like this. We have the transparency and cutaway not applied yet. So as soon as we apply the cutaway, we are able now to see clear the difference among the colors. And for the last step, we change the aperture angle, so we are able to have a bigger area around the primary object. Okay, what went well, we were able to provide both techniques for the both filters. The real-time solution works until we have 8,000 cells. Up to that, more than that, it doesn't work well real-time. So as a solution for this, we are planning to implement a part of the algorithm on the shaders, so we can address the scalability issue and also the discrete illumination. I'd like to thank you all for the attention.